Hello, good morning, good afternoon, or good evening. This is Jim McKeith. Thanks for joining us for day two of DelphiCon 2021. And you're here just in time for Olaf's session on multi-threaded programming on Apple's Mac M1 versus Mac Core i7 versus Windows Core i7. So this is the roundup of the CPUs and operating systems and how that affects your multi-threaded programming. So this should be a huge lot of great information because definitely something to be concerned about with all the new hardware that's out there today. And Olaf is certainly the guy to share that with us. So with that, I'll turn it over to Olaf.
All right, thank you, Jim, for the warm words. And yes, good morning, good afternoon, good evening, wherever you are. And again, it's time for some multi-threading on Delphi and some Apple and Windows devices here. So I have a lot of code to show, and this is my only slide. So if you want to contact me after the session, just send me an email, and email address is on the slide. And well, let's start into the session right away, and let's move over to Delphi. So let's close down the slide here. We don't need that anymore. And let's head over to Delphi. So before we actually go into the source code, I'm going to show you what we are going to develop and what the findings will be. So I created some multi-threaded application, and if you know me, you probably have seen me writing multi-threaded applications quite several times, and sometimes I'm pulling images from an external web service, or I'm just using Sleep to simulate some calculations that are going on. Here, the motivation was to see how Delphi and its compiler and its code would behave differently, or if they would behave differently on Windows machines powered by Intel processors versus Apple and Apple Silicon powered machines. So what I have here is basically it's a MacBook Pro. It's running an Intel processor. It's an i7. It's one of the newer models I have. Well, newer is relative in these times. And this is a 2019 MacBook Pro, 16 inches, has a i7 Intel processor. Okay, I'm good with memory. I have 64 gigabytes of RAM. So this is the typical setup for me or used to be the typical setup for me as a Windows developer with Delphi. So this is the virtual machine. I'm using VMware Fusion here, and VMware Fusion is running on that MacBook Pro. So this is my very simple application. And of course, even though I started out with a VCL application to do all my tests, I ended up doing a FireMonkey application because we're gonna run this on the Windows machine on a Intel Mac, and gonna run that on a newer MacBook Air M1 machine. And I have some pre-prepared screenshots from Matthias, who tested that for me on his MacBook Pro M1 Max. So we're gonna see what's happening here. So let's run the application on the Windows machine here. Just do that in Windows 32-bit configuration and see what the application does. It's a really simple application, and we're gonna look into the details of what it's doing thread-wise later. So I have a single thread test that's running in the background, and of course the window is still responsive, and that test took about 6 seconds, and it's running at a speed of 2.2 million primes per second. So I'm not using web service in the background to simulate work. I'm not using sleep. I'm calculating primes. I didn't write the algorithm by myself. I found something on GitHub. Somebody implemented the sieve of Eratosthenes in Delphi. I fixed a little bit of that algorithm. It has a couple of overruns, stuff like that. So in the source code that you will receive, there is a submodule for the Git repo, so you can even look into the prime calculation. So the idea is not to get the best performing prime crunching machine here or prime crunching application, whatever. It's just to do some work. And if you have ever taken some computer science classes, you probably had to write something with the sieve of Eratosthenes, and you probably know that it's quite fast when you have only a certain amount of prime numbers that you are interested in, but it uses quite some memory. So it's a trade-off between speed and memory always. And the sieve uses quite some memory, and of course it does some calculations. So what we see here is technically CPU cycles burning and memory input output. So it's a little bit realistic testing. We just want to burn some CPU cycles and see how it compares to different setups here. So it's not about figuring out how to calculate primes the fastest way. Okay, so we have 2.2 million primes per second on that Windows 10 32-bit process and running in a single thread. So we run that now with multiple threads, and as you can see, we have 8.8 million primes per second, which is quite interesting because it scales. It scales by the number of cores that are available in this virtual machine. I have 4 cores in that virtual machine, and the core number is detected correctly by the RTL. We will have a quick look later how that works. And if we look a little again, you see the CPU time walks up, and of course, depending on what's running on the system in background, the numbers are a little bit flaky sometimes. So it scales, as you can see, almost by the number of 4. So which is a great thing because I just calculate a lot of prime numbers in multiple threads, so there are no dependencies between all these calculations. So it's no surprise that it's scaling very well here. All right, so this is an i7 Intel processor, a relatively new one, just like 2 years old. So it should be pretty fast. And of course, some of you will say, oh, this is a virtual machine, so it probably executes slower if it would run on the actual hardware. So we can do that as well, of course. So we can compile the whole thing to Mac OS 64-bit in the Intel configuration. What I have here, we have to switch over to the actual Mac I'm using here, which is my MacBook here, and say save, and I'm going to run that. And oops, I have to activate the configuration, of course, and let's run that. Takes a moment, and we switch back to my actual Mac. This is the PA server running in background, and you can see it's doing some stuff here. So I'm using PA server to transport the application over to my real Mac or the host of my virtual machine. So here you can see I have 16 cores, which is basically what the i7 is. The i7 is a 8-core processor with 2 threads per core. So we have 16 cores that we can see. And you can see there is some stuff going on. It's basically the virtual machine that pulls some CPU time here, and let's see what the single thread does. Remember, we were at 2 point something for the Windows configuration, and here it's 10 seconds, or I'm sorry, it's 1.5 million primes per second. Just run it once more just to see if it's stable. So it's a little bit faster, slower. I'm sorry. So even though we are running this very same application and the very same algorithm on the hardware, on the bare hardware on the Mac, it's slower. Let's see what the multiple thread machine or thing does. So we are now at 14 million primes per second, which is not surprising considering that we have 16 cores. But if you think about it, we have 16 cores, and on the other machine, on the Windows machine, we have seen that it scaled pretty by the factor of cores that we had. So it should actually be somewhere at 20 something. So we don't see the scaling that we had on the Windows machine, which is probably because there is some stuff going on in the background. So it's not that bad at all, considering that this machine, it used to be quite expensive. So I had to pay for it like 5,000 euros because it has a 4 terabyte SSD and that 64 configuration, 64 gigabytes RAM configuration, and the basically the largest interprocessor available. So we can have a quick look at what the system says here. So it's actually an i9. I'm very sorry, I confused that. So it's an i9, the 2.3 gigahertz machine, and like I said, the 64 thing. So that thing used to be expensive, really expensive. So it's slower. Of course, the multi-threaded benchmark, if you will, has a better number because we have more cores, of course. But the single core performance is slower, which is interesting, which is probably because the compiler that we are using is using at certain situations pure Pascal instead of optimized assembly at certain points in the RTL. That's my guess why it's actually running slower on the Mac side if we are running on the same machine actually. Okay, so let's go back here and see what we could do with a ARM configuration. So I prepared a ARM configuration which is new with Delphi 11. In Delphi 11 we not only have macOS 64-bit but macOS ARM, which targets Apple Silicon, the M1, in other words. So I have to switch my connection, which is my MacBook Air, which is on the other side of my desktop here. And let's say save and recompile the whole thing and see what's happening here. It's compiling, linking, that takes a moment. And now just run the project, and I'm using actually, I'm actually using Apple's remote desktop application to show you the output or the screen of the MacBook Air that I have here. So let's see what machine that is. So it's a MacBook Air 2020. So it's one of the first M1 machines. It has 16 gigabytes of RAM and of course the M1 processor. So let's see what the single thread test shows. It shows 4.50 million primes in the single thread. So even though this MacBook Air was a relatively cheap machine. It was like 2,000, actually a little bit around $2,000. So it's running in a single core much more faster already. And see what the multiple threads give us. So here we see again, it's even a little more probably than just by a factor of 4. There are two things to observe now. Of course, this is faster than my really expensive MacBook Pro with 16 cores. And this little one here, just think of it, it's the MacBook Air, and it reports by the RTL 8 cores. This is not quite correct, or it has to be interpreted in some way. The architecture of the M1 is in the non-Pro and the non-Max configurations in the way that we have 4 high-speed cores and 4 efficiency cores. So in fact, we only have 4 cores then that perform the calculations that we can actually utilize in a non-energy saving world. So technically, it's running on 4 cores only, and it's still faster than my 16-core MacBook Pro configuration, Intel configuration, which is interesting. So here we have to keep in mind these 8 cores are not really the cores that are executing the calculations. I was not able to see or find on which cores we actually execute, but it should be the high efficiency cores that the M1 brings. And one more thing to observe is if you open up the activity monitor in Mac OS, this is the application that we are running here. It's this threading test FMX, and you see the kind is Apple. Apple means it's compiled as ARM or Apple Silicon executable. Okay, so it's really optimized for the Apple Silicon, that executable. There's one other thing now to see, and you see this is not something I create statically. I'm reading that from the RTL, and the RTL does not know yet that there is actually a platform on Mac, which is the M1. So that's something missing in the RTL. So that, of course, I could use an if-def, because if I compile my application, my application for ARM on Mac OS, it can only be executed on a ARM platform, on an M1 platform. But next thing to see is this. I'll just leave that one open here. And let's see what we can do here. So I can even create a macOS 64-bit Intel binary, and just let's compile and deploy that one. And interestingly, even though the Mac M1 is not using an Intel processor, we can still execute Intel code on it. That is something Apple created for us. It's the Rosetta 2 emulator. So they are running an emulator to execute Intel code. Okay, let's switch back here. So this is now the binary compiled as Intel binary. So we can see that here, this is the other one. This is the one that I just compiled and deployed here to my MacBook Air. So this is Intel code, and let's see what's happening here. So remember, this is running through a emulator. And if you compare that, there is almost no difference. So the emulator is obviously done in a very, very efficient way. So there are sometimes even some. It's so close that it looks like it's sometimes even running faster, but that's due to the fact that there is something running in the background sometimes. So let's do that again. See 1.16, do it here one more time, just quickly. And you see it's so close on a single core. On a single core, there is no difference really. And even on the multi-threaded test, it's running close to 19.2 million primes per second, which is basically what we see here as well. So it's the same number. So even if you are not able yet to compile for Apple Silicon, even if you compile for Intel, it's still executing very, very fast on the Mac platform. Okay, so let's have a quick look in comparison to what the bigger M1s bring. So I have some stuff created here. So remember, we are looking at 4 point something and 19 point something at or for the Apple binary. I have some pre-created images here. So this is what the same application gives us as on a M1 Max. That's Matthias MacBook Pro. And you can see the single core is basically the same. So the M1 architecture, and that's not surprising, is the same. It's just a larger chip. So they have 10 cores, 8 of them are high efficiency cores, and 2 are energy saving cores. And you see we have 32 million primes per second, which is basically the difference between the 8 and the 4 and the 8 high efficiency cores. So it scales not exactly, but you see we can utilize the more cores that we have, we can utilize and make use of it. So if you're looking just for single core performance, the M1 Max doesn't really help because it's the same single core that you have. It's just that you have more memory and more cores on the M1 Max and Pro, of course. And here's same, basically the same results for the Intel binary. The Intel binary is basically producing the same numbers again on the M1 Max. Okay, so what you can see here, single thread, the application is still responsive. So we are going to look a little bit in how to actually produce that application and how to run threads on whatever platform. Okay, so this is just a UI, and I have a simple timer. The timer is just looking at the CPU usage and the core count to get an idea of what we're doing here. On what we are running here. So let's have a look here what that's doing, update UI, and that's update UI. And I created a little bit of, or a simple class, a helper class that detects the platform and the actual CPU usage and the core count. How does that work? So the platform, this is a simple class that I created. And let's see how core count and CPU usage works. So we go to get core count and get core count. It's really easy. You just go into T-thread processor count. That's something that the RTL detects for us. And like you noticed, it doesn't really differentiate between the different kinds of cores that we now have. That's probably something that has to be brought into Embarcadero and make a feature request so that we would know that there are different kinds of processors. But that's something, it's still usable. It's still giving us the information which is technically correct. We have 8 cores in the M1, in the simple M1, and 10 cores in the M1 Max and Pros. So the number, of course, is correct. And then the current CPU usage, that's something you get through the thread pool. The thread pool is something that comes from system threading. System threading has all these parallel programming utilities that you would use to create tasks and threads in a very convenient way. And they have a thread pool statistics record. And there is some magic in the code that gives us the current CPU usage. Okay, so this is current CPU usage, and the description for the platform is something I create in a separate type, which is the T platform info record. And when it's running detect, it just uses the TOS version, which is a record or a structure inside sysutils. Sysutils has TOS version, and there is quite some information that you can use to display information about the platform you're running. And then you can see, you can check what architecture you're running on. ARM is unfortunately only for mobile platforms, so that's the reason why it's not working for the M1s yet. They are both, or the M1s are all reported as Intel X64 yet. So that's something that needs to be corrected by one of the next updates in Delphi, I guess. And compiled bitness, that's basically I wanted to display what did I use as a compiler. The 64-bit compiler in Windows, for example, is available as well. Of course, we have target platform Windows 64-bit, and we have Mac OS 64-bit, and there used to be a Mac OS 32-bit version as well, but Apple deprecated, or actually deactivated 32 bits quite a while ago. So native int is basically the number of, has always the number of bytes either as 32-bit configuration or 64-bit configuration. So it's 4 bytes in the 32-bit binary, and it's 8 bytes in the 64-bit compiler configuration. So if you want to know where you're running at, it's always the native int that you should look at. Okay, so that's system information. So let's go to the actual threading. Okay, this is system info. Threading is in here. So let's see how that works. Of course, there is no business logic in the form. So single thread, let's see what's going on here. Log starting single thread test. And here is the run single thread. T thread test run single thread. All right, let's see what that does. Run single thread. So this is basically a very simple class. It's my business class here. It does all the dirty work, and run single thread is what we are looking at here. So this is running in a background task. So I'm using T-task to do the actual work. That's the reason why my application is still responsive while it's working. So what we are doing here is the sieve of Eratosthenes and call get primes with max prime. Max prime is basically the maximum number that it should investigate. So it's running from 2 to max prime and checks which prime numbers are in that array. So max prime is a constant here. So we are looking into an interval of 1 million numbers to investigate if they are primes or not. Okay, and see how that works. It's basically really simple. We are just burning cycles in here. The actual implementation, well, it's not really interesting. It's thread safe, or actually I made it thread safe. The original code wasn't thread safe. And so it burns cycles by calculating, and it uses quite some memory. So we see some more or less realistic, well, use case here. And we do that a few times. Max tasks is 200. So we calculate the primes from 2 to 1 million at 200 times. And we take the time. And when we are done, we are sending a message. So I'm not, because we are running a T task here, we cannot just return the time used in that procedure or in that method, of course. We need to send a message, which is one of the possibilities to communicate from within a thread to the outer world. And we are using something I'm doing quite frequently, or I'm doing usually, and I'm using the T system messaging system, and there is a T message manager, and I'm enhancing that one by a method send message synced. So T message manager is not thread safe. So you have to make sure that the messages you are sending through are sent in the context of the main thread. And that's what I'm doing here. This is a quite common technique. I'm using a T-thread queue, which synchronizes the code in here, which is just the traditional T message manager, default manager send message. And it's putting that into a queue for being synced with the main thread. So it's returning relatively fast, so we are not blocking our actual thread here for a too long time. And we are sending that message into the system. And in the main form, how does that work? We have in the main form, there is form on create, and we are subscribing to two kinds of messages here. So we are subscribing to message single result and message multi-result. So that's basically the two types of results we are getting from the thread test mechanism. And it's obviously two buttons that we have. We have two buttons for a single thread and a multiple thread test. And these tests return different results. So to differentiate what it is, I'm using two different kinds of messages here. And we are subscribing to that message type, and when the message comes in of that type, this code is executed. And as we are sending the message in a synced way, we can be sure that this is running in the context of a main thread, which is required to update or communicate with the UI. UI must only be touched from the main or UI thread. So we are just logging that into the into a memo, and just well, using the message that's coming through here. It has a value, execution time, and that's what we are just visualizing here. So let's see how the actual messages are looking like. So we have a relatively simple declaration here. So it's a message single result and message multi-result, and both carry as payload a T-sieve result. And that's up here, primes per second and execution time. And we are creating that just down here. So this is the actual execution time, and here we create one instance of that T-sieve result record. We create that, give it the execution time, pass over the used max tasks and max prime numbers, so that it can do its own calculation for primes, mega primes per second, and the actual execution time. So that's just some simple infrastructure. Now let's have a look at the multi-threaded way of calculating. So this is relatively easy. Again, I'm using a outer T task. Okay, that outer T task is used so that the inner setup doesn't block the UI. So we just hit the button, run multi-thread, and the UI returns immediately and becomes responsive immediately again. And inside that outer T task, we are setting up the actual test environment, which is, well, of course, we're taking the time, the starting time. We are starting a loop, again, max task, and in every loop, we are actually executing another task. And that one is calculating the primes that we use to calculate in a sequence in the single thread test. Now we are calculating each set of primes in its own T task. So this runs from, well, let's see, from 1 to 200. So the question is now, would we see 200 threads created at almost the same time? Because this loop runs very fast. So we are creating 200 T tasks in a relatively short amount of time. And would that mean that we end up with 200 threads that are behind a T task? Would these 200 threads run immediately? No, they won't. T task is using a task manager, and that one basically creates only a certain amount of threads that are actively running. And to determine the number of threads that are running at the same time, it uses the available core count. So the available core count is multiplied by 4, and that's the maximum number of threads that are running at the very same time. This means we are not blocking the system by 200 threads running at 100% each, which would lead to a completely unresponsive system, of course. So we are just running a, well, call it a safe amount of threads with almost 100%, and the task manager that we are using in the background even watches if we are close to 100% total utilization in the system. And if we are close to 100%, it stops scheduling more tasks so that there is still room for some applications around me and even for the main thread. So T-task doesn't execute everything at once, which means if you created 4 threads manually, those would run immediately at full power and would utilize all 4 cores on this Windows machine completely, which leaves the main thread probably a little bit shaky or well, stuttering, because there is simply no more calculation or CPU cycles available. And T-task avoids that by looking at the system's total utilization. So we are using that task manager in the background, which uses a thread pool, of course. So threads are not recreated completely. They are taken from a thread pool. And of course, now we have to wait until all of these 200 tasks are done. And for that reason, I'm using a simple array. This is a TA array of iTask. It's an interface type that is returned, but once you start a new task by run. So it returns a new instance of a T task, and I'm putting that into the task array. And here you can just say T task. So I'm using a class method saying wait for all tasks in that array to be completed. So this means this line blocks until all 200 tasks and its corresponding threads are finished. And this is also the reason why we really need a outer task, so that we don't block the whole UI. If we didn't have that outer task, of course, then we would block this whole operation would be a blocking operation, and it would block the UI, and the UI would become unresponsive while calculating the prime numbers. So we wait for all the tasks, and now it's just some basic calculation here, and that's the way how the multi-threading is set up here. So to summarize, we can create code for Windows and in 32 and 64-bit configurations, and of course we didn't see that yet. So let's have a quick look at the 64-bit configuration to see if it makes any difference. So single-threaded, we were at 2 point something with 32-bit. Let's see what's happening here. We are a little bit below 2 point, what we have seen was 32 bits. And let's have a quick run with the multiple thread thing. And you see it's also a little bit slower. That's due to the fact that 64-bit doesn't necessarily mean faster. It just means you have larger containers, if you will, larger containers for your variables. So there is more memory associated with the structures that you are carrying around. That means you have to work a little bit more to do all this same stuff that you are used to do in 32-bit mode. So 62-bit, 64-bit doesn't really mean faster. Keep that in mind. You only have more memory available, and your variables are a little bit larger, which means that there is more calculation time required sometimes to execute everything. And this is quite consistent. If you run this more over and over again, it's basically showing the same numbers. It's a little bit slower than running the same thing on 32-bit, which is surprising, of course, if we look at the 64-bit executables that we created for Mac OS on ARM and Intel. We noticed that 64-bit on Mac OS is slower. So it could be the 64-bitness, and it could be that certain things are not that optimized on the Mac platform. And if you now compare that to the ARM 64-bit executable that we have seen, which is way faster, or a bit faster than what we have seen in Windows 32-bit, it's quite amazing that this Apple silicon is really that well effective in terms of performance, memory-wise, and CPU cycle performance. So that's basically what I have to say for the sessions. I hope this was a little bit interesting for those of you who didn't really look into M1s yet. So again, this Delphi is running on an Intel machine, but the PA server that we have seen here is already running on the M1 platform. So this is the PA server that we have used, that we can compile happily to both environments. Let's see where it is, threads. So we can compile for ARM and Intel, and both execute really amazingly fast. And it's really cool to see what Apple did with the M1s, and it's probably something we will work with in the future quite frequently. So that's my session. Again, if you have any questions, we have a little bit of time right after this. And of course, you can send me an email at olaf@monien.net. All right. Thank you very much. And well, Jim, you still there? You fall asleep, or you started coding? So let's see what we have in terms of questions over here. There are a couple of questions. Okay, let's open the question window. Okay. All right. Good afternoon from Europe. Yep, it's already afternoon here. Okay, Bruce McGee says, no, I'm suffering from laptop ennui. Yeah, you are, and me as well. So yeah, it's gonna be not easy. If you need a new one, do you go into Apple all in with M1s? Well, I mean, the results are really amazing, I believe. Well, Francois asked what exact one i7 processor I have. I just showed the information screen on my Mac here, so it's actually an i9. Of course, I mixed that up with my previous Mac model, so it's the 2.3 gigahertz version of the i9. And the code will of course be available. That somebody asked, and what we have. So only 8 actual cores. So the M1 in the MacBook Air has 8 cores. 6 of them are the 4 of them are the high performance ones, and 4 of them are energy saving cores. From Roland says, from what I found, the compiler optimizer seems to be inferior for macOS and Linux to that of Windows. Yes, that's probably true. We often even see that if you look into these so-called fast routines, that there is usually pure Pascal if you even run on 64-bitness. So it's not using the optimized things, and that's not even a compiler thing, that's a language thing. Did I saw i9 for the computer? Yes, that's i9. Maybe Mac is slower because you are comparing against the 32-bit Windows version. Yeah, that's what I basically said at the end of the session. It could be 64-bit bitness of the Mac OS binary that I'm creating. I cannot compare against the 30-bit binary for Mac OS because we don't have that anymore. We can't run that anymore. And as you see, the 64-bit one is on Windows still faster than on the Mac. You call a $2,000 computer cheap? Well, it all depends. This is my working machine. I used to work with that MacBook, this expensive one, and even the MacBook Air, and well, it's my business, so it's a tool I pay for it. Of course, if you just use it to do some Facebook browsing, it's really too expensive, I guess. But there are still cheaper ones than the one I have here. What is the clocking in gigahertz of each CPU? Well, we have the clocking of my MacBook Pro 16 inches here. That's 2.3 gigahertz, and the clock on the M1 is not specified actually in the system information screen. That's something I would have to look up at somewhere at Wiki or wherever we could find that. I'm actually not sure what clock speed we're using on the M1s. Couldn't the difference between due to the compilers? Of course, it's somewhere between the bitness and the compilers. For Windows 32-bit, we are using the classic Delphi compiler, the DC32 one. And for Mac, we are using the LLVM infrastructure, which is completely different. It's probably not that optimized as the compiler, the 32-bit Windows compiler that has evolved over the past 25 years. Let me see, Francois, on screen you show 2 times the Intel version instead of the Intel. Yes, that's something the RTL is not able yet to detect. So even on the ARM, even if we are running the ARM version, and you see it's the ARM version which is running right now here, you see its kind is Apple. It's still saying Intel's X64. That's something that needs to be fixed in the RTL. We cannot detect that yet in the RTL. Yeah, same question from Gran. Ian Barker, watching Olaf write code is like seeing a poet. Yes, thank you. I always try to my very best to produce code and show code that's interesting to to you. So I'm happy if you liked it. Thank you again. Where can I download your example? I guess Jim is going to post some links. I will post it on my blog as well. There will be a zip download, but I guess all the source code downloads for DelphiCon will be available through Jim. He will provide URLs, I guess. Same question from Grigor. And again, it's the demo. Yeah, source code will be available. Okay, Hans is saying 64-bit should be faster if you are running double as real time. To be honest, I'm actually not using a lot of floating types in the prime calculation. It's basically all integer math that's behind that. So I doubt that this would speed up anything here. Of course, you are free to look into the source code of the prime calculation of the sieve, which again, I didn't invent that. It's a known algorithm, but you are of course free to look at it and see if there is anything that they could do 64-bit wise. Yeah, 64-bit numbers will use CPU cache faster. That's something that Roland is saying. Yes, that's true. That's because these structures are just larger, and that's why you only have, or it's twice as large as 32-bit variables, if you will. So it's using up the cache faster. That's true. Okay, interesting session. Thanks. Again, I'm happy if that was a good one. How much faster would it be for M1 Pro and Max? You guess. Well, I've shown the results from the M1 Max, which basically show that the single thread is the same number, and it's faster only on the multi-thread testing because we have more cores, and the algorithm I'm using is scaling very well, so we are seeing better numbers on the Max because of the number of cores. The Pro and Max shouldn't be really that different, I guess. Source will be available. Thanks again from Sebastian. Let me see. Why 200 threads and not one thread per core? Well, Frank is asking why 200 threads and not one thread per core. Basically, it's 200 tasks, and the thread manager behind, or task manager behind, looks at the available cores and only produces or lets run a certain number of actual threads depending on the available number of cores. It won't be 4, it will be probably 16, because there's always some context switching, and of course you are free to tune the number of threads that the thread manager would use. That's something that you can actually adjust. You have access to the thread manager that is used by system.threading. Hi, you have an i9 and not an i7. Yes, sorry for that again. Is there a way, Frank is asking, is there a way to select if a thread would run on a if it's running on the Firestorm or the Ice Storm core? So Apple has these high performance and the energy saving cores. The high performance cores are called Firestorm cores, and the energy saving cores are called Ice Storm cores. And so far in the RTL, I don't think there is a way to detect that. It's something I will certainly work on and see if there is something that could be done. But for now, I don't know. It's probably a way, or there is probably a way to do that if you are running or using any of Apple's libraries. But that's something I couldn't figure out yet. Intel processors have generation. I think Mac use ninth generation, which is quite old, not fair to compare with a brand new M1. Yes, of course, it's 2 year old, and 2 years maybe quite a lot. And the i9, yes, it's definitely an older architecture, but considering if you bought a high performance CPU just 2 years ago and compare it to a relatively cheap CPU like the one in the MacBook Air, I don't think it's that unfair. Of course, there are differences you have to know about. The M1 is in a 5 nanometer process, and the i9 is a 10 or even a 30 nanometer process. So yes, it's a different generations for sure. It looks like you are running iStat menus on your Mac. Yes, I do. Yes, I could use that one and see what every core does and what it doesn't do. So I didn't experiment with that one yet. Good idea, actually, to do something on that. Is your friend, Joe is asking, is your friend with the M1 Max running Delphi with parallels? No, well, yes, of course, Matthias is running Delphi, but I gave him pre-compiled executables so that these executables are really the very same ones that I'm using here, so that there is not a difference because Matthias uses some internally already optimized Delphi version or something like that. So Delphi itself is, of course, already usable on the M1s by using parallels. So I guess the question is actually, can we run Delphi on the MacBook Air? Yes, we can. I can't show it yet because my machine is not set up on that machine. I've seen several screenshots and videos where Parallels 17 executes Windows Windows 10 ARM, which is still in not even beta. It's in insider preview. So, and in that Windows ARM, Windows ARM version, you can actually run the Delphi IDE, and Windows ARM brings again a simulator, or it's an emulator for executing Intel binaries, which is the Delphi IDE. It's obviously an Intel binary compiled executable. And that one executes on the ARM version of Windows because Microsoft has an emulator that executes that Intel code on the M1. And that works even a little bit faster than running on a native i9 MacBook Pro. That's what I can actually say. Okay, George, we have only a minute or so left. Let me see if there is anything which is important here. Source code available, yes. Percentage, but how much faster is M1 versus Intel? Well, you have seen the numbers. It's easily 30% faster, I would say. Can we use Delphi on M1? Yeah, I just talked about that. All right, so I guess I believe we have every question, almost every question answered. If there is anything important left over, just drop me a note by email, and I guess I have to return it to Jim for the next session. Let me
All right.
see where.
Yep.
Here you
I'll just
are.
start next session. Yep, I'm here. So thank you so much, Olaf. This is great. Looks like everybody enjoyed it, and we'll see everybody in the next session.
All right. Thank you. Bye-bye.
Bye.